जनगण जय हे भारत भाग्य विधाता, पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा, विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा, तव शुभ नामे जागे।
What is audible?
Yes, sir.
No, it is not audible here.
செயலினை மூச்சினை உனக்களித்தேனே நைந்தாயனில் நைந்து போகுமென் வாழ்வு நன்னிலை உனக்கெனில் எனக்கும் தானே முந்திய நாடினில் அறிவுமில்லாது மொய்த்தனன் மனிதராம் புதுப்புனல் மீது செந்தாமரை காடு புத்தது போல செழித்த என் தமிழே ஒளியே வாழி செழித்த என் தமிழே ஒளியே வாழி செழித்த என் தமிழே ஒளியே வாழி.
The live telecast, it is over.
Okay. Okay, sir. Okay, sir. Thank you for the soulful invocation. Thank you for the soulful invocation. We now invite our convener, Dr. M. Venkatesan, Associate Professor and Head of the Department of CSC. Venkatesan, Associate Professor and Head of the Department of CSC, to deliver the welcome address.
Good evening to everyone present here. On behalf of the Department of Computer Science and Engineering, National Institute of Technology, Puducherry, it gives me the immense pleasure to welcome you all to the inaugural session of IBM Qiskit Fall Fest 2025, being organized from 17 to 19 November 2025 in virtual mode. First and foremost, I extend my heartfelt gratitude to our director, Dr. Makaran Madhav Gangrekar, for his continuous encouragement and visionary leadership. I also express my sincerest thanks to our registrar, Dr. S. Sundaravardhan, for his support in making this event possible. We are greatly honored to have with us our chief guest, Dr. Dinagaran Vinayaga Murthy, Staff Research Scientist and IBM Quantum Ambassador. Sir, your presence adds immense value to this fest, and we look forward to your insights that will inspire our young minds to explore the transformative world of quantum computing. I also take this opportunity to acknowledge the guidance of Dr. G.S. Maghabatra, Dean Research and Consultancy, whose support has been instrumental for our department initiatives. Quantum computing is redefining the boundaries of science and technology. Platforms such as IBM Qiskit, which is platforms such as IBM Qiskit, which are enabling students, researchers, and developers worldwide to experiment, innovate, and contribute to the quantum revolution. Organizing the Qiskit Fall Fest at NIT Puducherry is a proud moment for us, as it reflects our institute commitment to emerging technologies and cutting-edge research. Over the next 3 days, participants will have the opportunity. To engage in hands-on sessions, workshops, and challenges and discussions. That will encourage all students and research scholars efforts in putting this event together. Once again, I extend a warm welcome to all the dignitaries, experts, faculty colleagues.
Significance. We extend our sincere thanks to our patron, Dr. S. Sundaravardhan, Registrar, for his guidance and unwavering administrative support, which has greatly strengthened today's program. Our heartfelt appreciation goes to Dr. G.S. Mahabatra, Dean, Research and Consultancy, for gracing today's ceremony and sharing his valuable insights. We are truly honored to have our chief guest, Dr. Dinakaran Vinayakamurthy, Staff Research Scientist and IBM Quantum Ambassador. Sir, and a special thanks to our convener, Dr. M. Venkatesan, Associate Professor, Head and Department of Computer Science Engineering, for his warm welcome and for his continuous support and encouragement throughout the planning of this event. And we are equally grateful to our coordinator, Dr. B. Surendran, for presenting a clear and enlightening overview of the Qiskit Fall Fest 2025 and for guiding the academic direction of this program. A heartfelt thanks to all the faculty members, research scholars, student volunteers who dedicated efforts behind the scenes have helped make this inauguration seamless and successful. And we extend our warm appreciation to all our participants joining from various institutions across the world. Your enthusiasm and presence truly enriched this event. Finally, our sincere thanks to the anchors Divya Bharti and Nageshwari, research scholars from NIT Puducherry, and the technical team, Ayon, Uday Prasad, Sri Hari of finally CSE, the media support team, and everyone who contributed directly or indirectly to the success of this ceremony. Once again, thank you all for your valuable time, support, and participation. We look forward to your active involvement in the upcoming sessions over the next 3 days. Thank you and have a wonderful and insightful Qiskit Fall Fest ahead. Thank you.
Thank you, sir, for your heartfelt acknowledgements. We request everyone to stand for national anthem.
पंजाब सिंध गुजरात मराठा द्राविड उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Uh, national mantle is over. Kindly be in the line. The once the chief guest starts, will inform. Thank you, everyone. The inaugural session is over now. Participants be in online.
With great pleasure, we welcome our chief guest, Mr. Dinagaran Vinayagamurthy, Staff Research Scientist and IBM Quantum Ambassador. Mr. Dinagaran serves as a key contributor to the advancement of quantum computing in India, holding the prestigious role of manager of the Qiskit India team and acting as a senior IBM Quantum Ambassador lead. He is a distinguished researcher within the Quantum Computing Research Group at the IBM Research India Lab in Bangalore. His responsibilities include managing the critical IIT Madras IBM Quantum Partnership, fostering academic and industrial collaboration in the field. His core research interests span several frontier areas of quantum security and resilience, including quantum error mitigation, cryptography, and security. During his tenure at IBM, he has also made significant contributions to projects involving blockchain interoperability, encrypted databases, and privacy preserving machine learning. Coming to his academic background, Mr. Vinayagamurthy holds a PhD from the University of Waterloo, where he was affiliated with the CRISP Group and the Institute of Quantum Computing, advised by Dr. Sergey Gorbunov and Dr. David Zhao. Prior to his doctoral studies, he obtained his master's degree from the University of Toronto Theory Group, advised by Dr. Vinod Vaikundanathan. His academic foundation began with undergraduate studies at the College of Engineering, Guindy, during which he gained valuable experience working under Professor Pandurangan at IIT Madras. His professional experience is further augmented by internships at major research institutes, which includes Microsoft Research Labs in India and Cambridge. Mr. Vinayagamurthy is recognized expert in his domain, holding several publications and patents. Now, I would like to call upon our chief guest, Mr. Dinagaran, to deliver his address. Sir?
Yeah, can you guys hear me?
Yes, sir, we can hear you.
Okay. Okay, great. Thank you. Thanks a lot for the invitation and for the introduction. And it's great to see a very significant participation here and the interest in quantum computing. Since I had been traveling, I could not, let's say, share some slides in my laptop and then do a longer presentation. But I thought I will take the opportunity to, like set the lay of the land in quantum computing to see where is that you can strive towards and what is that you can try to learn and then do in the next this week and then also going forward in this area, right? Just to get a quick pulse check, so I see about 70-80 participants. So just to make it active, how many of you are, let's say, from the computer science background? How many are from the, let's say, physics background? If you want, can you just post on chat? Or chats are disabled, I guess, right? Or is it available? Okay. Okay, good. So I think what I can see is that there is good participation across computer science, ECE, and some physics. Okay, good. So I think you will ask the question of, okay, the first thing you should ask is why quantum computing and what is that we can try to do beyond the computers that we can use today, right? So the larger goal is that, there are these very powerful computers that exist today, and where we see quantum computing to be useful is that there are certain problems that we can solve, significantly faster than the most powerful supercomputer that can exist today, right? So quantum computing is a new type of computers built based on the foundations of quantum mechanics, okay, which is actually the reality of how nature exists, how nature behaves. And till now we have extensively used quantum mechanics in many of the things that we use today, like for example our MRI scans or lasers, or for certain kinds of accurate microscopes and so on. So and for various polymers, so we have used quantum mechanical principles for various things that we use in our day-to-day basis. It has generated tens of trillions of impact. But the expedition that we are on taking over right now is to build and use general purpose computing devices based on these quantum mechanical principles. Okay, so very similar to the kind of devices we have today. And while building the computers, we are also doing research on what are the things that we can do in these computers more than what we can do in our existing supercomputers. Okay, so on that front, I believe over this week you will see some of the foundations of quantum computing that you will learn, and hopefully you will also learn about some of the applications of quantum computing. Okay, so thanks for the NIT Puducherry team to organize this. We are one of the very few shortlisted institutions from across India and from across the world to be running this Qiskit Fall Fest. So I would expect this week to be a great learning experience for all of you to get into the basics and then try to explore beyond uh, the basics and level up in quantum computing. Okay, and one of the things I would like to emphasize is that it probably is worth doing a full lecture in what is possible. I was initially planning for that, but I couldn't reach the destination soon enough that I can use my laptop. But one thing I'll emphasize is that even the most advanced content is available for free, right? It's all available in terms of the software to use as open source. There is free amount of quantum computing platform available for you to use, and then all the learning content from the very basics to the most advanced state of art research is available publicly online, right? It's in your limits. It's the limits that you set about how much you can push, and build on top of the basics, go step by step, and then learn the advanced things, because this is going to be the future of technology. So it's up to you and your interests to push to your limits and then learn to the best extent. Okay, so with that I will leave it to you and the regular sessions, and maybe I can also take some questions if you any of you have any. And anyway, think about it. This is just inaugural session. You will probably hear more of the details. But if there are any high-level questions, if there are any 2-3 questions that you want to ask, I'm happy to stay back and then answer.
Hello, sir.
Yep.
Hello, sir. Are you hearing me, sir? I am Dr. Gurunath from Raichur.
Yeah, I can hear you. Yeah.
Sir, so how that already we are very much fast in communication by using optical fiber, then how this quantum communication help to speed up the communication?
Okay, so I think my focus is more about computing. I haven't really, let's say, I'm not an expert in quantum communication. But one of the things that the research that's explored in quantum communication is not really about the speed, but more about the secure version of the regular communication, right? But maybe I will defer that to a future talk, because I will maybe answer questions more around quantum computing more than communication.
Okay, sir. Thank you, sir.
Good evening, sir.
Yeah.
How the quantum computing facilities will be equally available to mobile devices, sir, like servers, computers we are using. How equally it will be available for the mobile devices, that I want to know, sir.
Uh, so you should think about using quantum computers in a somewhat a similar spirit to how we are using supercomputers. Okay, because there are certain scientific computations at massive scale. Expect the use. The major applications of quantum computing you should try to think in parallel to how we use supercomputers. So it's not very clear what is useful that we can gain out of using it in mobile devices. So it's your bet. Maybe you can think of it like using it through a computer client and then running computations in the supercomputer. I mean the quantum computers over cloud is how we expect it to happen in the near future at least.
Thank you, sir.
Any queries from participants?
Okay, good. So if there are not any more questions, yeah, all the best for the rest of the sessions. Hope you guys learn from this and then also make the best use of the learning resources available and the compute resources available. And I'm really hoping that something you pursue this. Some of you pursue this in the future, and then yeah, hopeful to see some interesting contributions to the research and development from some of you. Okay. All the best. Thank you.
Thank you, sir, for your inspiring and enriching keynote. Now, I request to all the participants to join for the technical session at 7:30 p.m. We share the new.
Hello, sir. Good evening. This is Vijay Venugopal. I have one question. Hello, am I audible?
Yes, sir. Yes.
Okay. Yeah, ma'am. One question is, along with this technical session, right, in the next 3 days, will you be covering the NIST framework, right? NIST standard for the cryptography things, or that will be not part of this sessions?
Framework. Sir?
The
Can
NIST.
you please?
Yeah, post-quantum cryptography. Okay, I'm talking about post-quantum cryptography
Yes, sir.
topics. Is it part of this technical session, sir?
Sir, the session is actually the day one we plan to conduct for basics of quantum computing. And day two, it's all about quantum algorithms and its implementation. And day three is going to be quantum hardware and the remaining part of the quantum machine learning. So we are not going to talk about the quantum post-cryptography because we don't have that much time. Like.
Got it. Okay.
So we want to make sure that basics to QML participants need to know about these things. That's all. Like we restricted ourselves.
Got it.
We initially planned for 5 days since right from speaker and everyone. We got a speaker from very recently, only, like last week only. Everyone confirmed their talk by last week, so that is why we restricted.
No problem. No problem, sir. For the QML, will there be any hands-on or any?
It will be, sir. QML session will be handled by Dr. Nyal and another person from CDAC. So they will provide you hands-on, and at the end of it, you will be getting some quiz also.
Appreciate it. Okay, thank you.
Thank you, sir. Thank you.
Hello, sir.
Good evening.
Hello. Sir, good evening, sir. Myself, Dr. Gurunath.
Yes, sir.
From Raichur, Karnataka.
Go ahead, sir.
Sir, my students specially joined for understanding that Qiskit, and they have an experiment, and they are engineering level student.
Okay.
So see that students should understand also. That way, if you manage, then it is very good, sir.
Sir, that is why by tomorrow the sessions are handled by only the third year and final year students.
Mm-hmm.
Okay.
It's good, sir.
That is why we planned accordingly, so that students can easily understood, and in what way they understood, they will make sure that it will be understood by the engineering background level students also. So
exactly, sir.
Tomorrow, kindly attend it, sir. You will know. Of course, the sessions are going to be very simple and most technical also, because the presentations are about fully technical, and they came out with wonderful Qiskit development, like all the algorithms. So tomorrow you will see, you will be amazed to see the sessions.
Okay, sir. Okay. Looking forward for better, sir.
Inauguration, we had a people from IBM, and the first session was started by Dr. Nolan, who is the CTO from Data Tech AI. But we wanted only the budding engineers or budding quantum engineers to talk about it, who can talk about it much more than the people who is in industry.
Right, sir. Okay, yeah, sir.
Because they are currently doing research and they are currently working on quantum algorithms and everything. That is why.
Okay, sir. Thank you, sir.
Thank you, sir. Thank you. இல்ல அங்க போய் ஒரு ஆக்செப்ட் பண்றது. ஜூம்ல ரெஸ்ட்ரிக்ஷன் இல்லையா சார்? மியூட்ல ma'am, shall we start?
Session, or I can say like in this particular period, in this particular hour, in 1 hour of time given to me. So I would like to focus more on the fundamentals of quantum computing. So in the previous session taken by Dr. Dinakaran, we have already seen the importance of quantum computing or what is quantum computing and stuff like that. So in this particular 1 hour session of mine, I would like to contribute, or I would like to keep my knowledge or present my knowledge in the realm of these fundamentals of quantum computing. Like what exactly is quantum computing? Why do we require quantum computing? And all that is. And then I would like to slowly talk about some of the important topics or stuff which we actually require in order to work with quantum computing. So that you guys will be acquainted with those terms and use these terms in the upcoming sessions to make your foundations stronger in the realm of quantum. Cool. So yeah, I'll be taking the session for something like 1 hour or approximately like 50 minutes or something like that. And remaining time I'll be using to clarify your doubts or something. So if you have any queries or anything, feel free to ask me, completely not a problem. And feel free to just drop them in the chat box. I'll be very happy to explain. Okay, so yes, that's the deal. Let's start with the first slide, which is, you can see here, introduction to quantum computing. So what exactly do you mean by quantum computing? So simply to put, here you can see the quantum computing represents revolutionary paradigm, that, this and all. But simply to put, let me just bring it in a very straight way is that when we are talking about quantum, it is nothing but a classical computer works. Okay, before directly going into quantum computing, let me start with how a classical computer looks like. A classical computer works with the logic of classical bits. So that classical bits has an ability to be in 0 or to be in 1 state. So we will also call it as a Boolean logic, or we will also call it as the deterministic nature of a computer. Meaning, for example, for a particular thing, like for example, if there's a fan. So if there's a fan, there's only one way a fan can be. Fan can either be in an on position or it can be an off position. It cannot be in an on and off position at the same time, right? So that is my classical computer. So those are my classical bits. They can be in 0 or they can be in 1, but they can't be both at the same time. And that's the reason we will call it as deterministic in nature. So this word called as deterministic is a key term, as it is been coined by Newton and Einstein itself. As per Newton, every action, or no, I'm not talking about Newton's third law where it goes like every action has equal and opposite reaction. No, I'm not talking about that thing. I'm talking about one another thing given by Newton, which says that every action which is being done at this point of time can be predicted or can be judged or can be calculated by clearly seeing and observing the patterns on how it is actually moving in the past. Meaning, for example, at this point of time, a pen fell down. Let us consider. Now, as per Newton, I can go like, as the pen falls down at this point of time, I can say like, if I do 10 seconds before, if I go back before 10 seconds, based on the position of the pen and based on the movement of my hand, I can clearly see or I can clearly define that pen will fall in next 10 seconds. So that is my Newtonian theory, or that is my Einsteinian theory. Meaning I can see how a particle behaves by observing its pattern very nicely or very keenly. That's the concept. And that is called deterministic in nature. Again, that's what we'll be calling as deterministic in nature. Now coming to quantum computer. What exactly will happen in quantum computer? Okay, before directly going into quantum computer, I'd like to say one another concept. So this deterministic nature, this bits nature and all the stuff are there. Na? All these are directly just one prime concept, and that concept is called as Newtonian physics or Einsteinian physics. For example, let us go with a computer again. How a computer is working. For example, if I press a key called yes in my keyboard, how that yes is being displayed in my monitor? What is the entire physics behind it? The entire physics behind this is signals-based logic, temperature-based logic, and some electricity-based logic. So all are some basic principles of physics which are making all these things happen, right? So all these basic principles of physics are there now. So all these comes under something called as classical physics, or something called as Newtonian physics or Einsteinian physics. So that's one another thing of my classical computer. Classical computer works with classical bits, which can be in 0 or it can be in 1. Okay. And the second thing is it is deterministic in nature, meaning I can see or I can determine how which position can be. And third thing is they all work with classical physics rules, meaning the electrical, the temperature, and all that is the entire CPU works with classical physics rules. So that's the main deal about my classical computer. Now coming to quantum computer. In quantum computer, what will happen is instead of bits, we will be having something called as a qubits. Qubits ka matlab quantum bits, QU bits. What is the specialty of this qubits? Very simple, very straightforward, very easy. The deal directly goes like this. A bit can be in 0 or it can be in 1. That is like my fan, either on position or off position. That's it. But when you're talking about qubit, what happens is that can be in 0, completely alright. That can be in 1, completely alright. And also, it can live in something called as a superposition state of 0 and 1. Meaning, fan is on or fan is off, completely alright. But fan can also be in a state where it is both on and off at the same time. That's what will happen when I'm talking about qubits. Okay, meaning it can be in 0 position, it can be in 1 position, as well as it can be in a superposition state of 0 and 1. What do you mean by superposition state? Combined state of 0 and 1. And then it is on and off both at the same time. A cat is alive and dead both at the same time. You are there here as well as you are there somewhere at the same time. That is my superposition nature, and that is one nature talked about my quantum computer. Okay, now got it. This is just one principle of my qubit, or I can say like quantum bit. The second position, the second phenomenon is,
Sir, screen moving.
I am not moving, sir.
Yes, okay.
Because, yeah, it's still in the first thing only. I'm going into second paragraph, sir. Okay. Now, second deal is the nature of probability. So when I'm talking about classical computing, I talked about deterministic in nature, right? Why? Because I can find how it actually behaves. Now, when talking about quantum computing, it is probabilistic in nature, meaning I can find the state of a particular qubit by observing its probability. I cannot determine the actions when I'm talking about my qubits or when I'm talking about my classical computer. In classical computer, all that is important is my probabilistic nature. Meaning, for example, if I have one thing, if I have a qubit called A, classically, I can determine the qubit's position A. I can determine the position of the qubit A. But when it comes to quantum computer, I cannot determine it. Why? Because it is non-deterministic in nature. The quantum bits and the quantum state is non-deterministic in nature, meaning they are probabilistic in nature. I have the probability to be found or not. I won't be having the what can I say, deterministic nature. I'll be having the probability to find that particular state. So that is one another principle of the quantum bit. And they behave based on quantum phenomena, meaning quantum physics. Obviously, that's the way the name came as quantum computers. Obviously, everyone know that. So classical computers behaves with classical physics, meaning internally the classical physics is happening. But when we're dealing with quantum computer, internally the quantum bits are happening, meaning the physics of the quantum is being happening in the backend. What do you mean by physics of the quantum? Or why exactly it is different than classical computers? Very simple, very straightforward, and very easy. When I'm talking about classical computers, it is classical physics, meaning the behavior of the particle or the behavior of a bit or the behavior or the electric behavior of all the these all comes under my classical phenomenon. But now, on the other hand, when I'm talking about this quantum stuff, they all behave with respect to my quantum. So what do you mean by quantum behavior? Okay? I would like to kindly everyone to mute themselves. In case of any queries, please add this. Yeah, thank you. So yes, coming back. So the quantum computers will work based on the quantum physics. So what exactly is this quantum physics? First, before going to quantum physics, we need to know very well or very clear about the quantum world, the word called quantum. What exactly is this word called quantum? Very simple. Quantum means very small in nature. Okay, quantum meaning is small word. So what do you mean by quantum, or what do you mean by quantum physics? The physics which is being followed by small particles are called as quantum physics. The physics being followed by small particles are known as quantum physics. What do you mean by small particles? Very simple, very straightforward, and very easy. The meters are like below Fermi. So Fermi is approximately 10 to the power of minus 15 or 14. Now, if you go beyond that, like 10 to the power of minus 20, 10 to the power of minus 24 or stuff like that, there we will see the opening of the quantum. In the quantum world, so some of this about atomic, subatomic particles, which I can say are being a part of the quantum world, are your electrons, neutrons, protons, quarks. So all these things comes under the particles belonging to the subatomic world, or I can say like the quantum world. So these particles will not behave based on classical physics. They all behave based on something called as a quantum physics. Why it is completely different? Very simple. When you go to quantum, or when you are going into quantum nature or quantum basis stuff, what happens is that the physics will be changing, meaning the concepts of superposition, entanglement, and coherence, decoherence, interference, so everything comes into play when you're dealing with the quantum world. So that's why we'll call it as a quantum physics. It is completely different from your classical physics. Now, the qubits of the quantum computer, they behave based on quantum physics principles. So the qubits of my quantum computer behave based on the principles of my quantum mechanics and quantum physics. Got it? So that's the primary thing about my quantum computers and quantum physics. Now comes the next deal. So we already saw about all these things. Now, yeah. Okay. So now comes the next deal. Why we require quantum? Why we require quantum? So, okay, everything is good. Quantum computer, quantum physics, quantum bits, blah, 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 quantum everywhere. Why we require quantum? That's an important thing coming into play. Very direct answer. Just because of this principle of superposition nature, where I explained you that one clean concept, that concept is a classical bit can be in 0 position or 1 position, right? But when I talk about quantum bit, I mentioned that the quantum bit can stay in 0 position, 1 position, as well as 0 and 1 position, right?
Sir, excuse me, sir. Sorry to interrupt. Sir, your slide is not changing.
Sir, I did not change the slide yet, sir, because everything what I'm telling is there in this particular slide online.
Okay, sir. Okay, then. Okay,
yeah,
thank you.
Thank you for that. Now, so when we are dealing with this particular stuff, what happens is that because of this concept of superposition nature, all the things or all the advantages will directly come into play. Okay, so what exactly will happen in the superposition nature? Simple. Now just keep that superposition thing in your mind. Let's go back to our classical bit versus quantum bit. As I already mentioned, classical bit mein, you'll be having either 0th state or 1 state at a point of time. And the output is deterministic and predictable in nature. And we'll be having just one piece of information. That's what I mentioned. Either 0 or 1. That's it. Close. Just one piece of information will be provided when we are dealing with the classical bits. But on the other hand, talking about quantum, we are having two pieces of information. Or instead of saying just 2 pieces, I can say more than 1 piece of information. So what exactly do you mean by more than 1 piece of information? Very simple. They can exist in 0 or 1, both at the same time. So they can exist as 0 and they can exist as 1, or they can exist both as 0 and 1 at the same time. And comparatively, it is not deterministic in nature, it is probabilistic in nature. And as I already mentioned, infinitely many information, or I can say more than 1 piece of information will be provided when I'm talking about my quantum. Okay, now Mathematically, okay, so here my latex content is not rendered well. So obviously I try to write it in latex, but it's okay, it's not showing up. So, but I will tell it through my audio. So try to focus on that. So mathematically, I will determine a qubit like psi equal to. So psi is that symbol which you can see like a Trishoolam one. So psi equal to ket alpha plus, or I can say alpha ket 0 plus beta ket 1. So what do you mean by ket? Okay, I will write that in a chat box so that you can see on it. So I cannot write the alpha and beta thingy, so but I will write the psi values. So psi equal to alpha 0 plus beta.
Hello, sir.
Yeah,
Sir, if possible, use whiteboard, sir. Better understanding.
Whiteboard. Okay, I will do that actually. So that's actually very clean way. So I will share the entire. Now, okay. So when I'm talking about quantum, so this block sphere is there, right? The thing which I'm mentioning. So the superposition state which I mentioned. The superposition state which I mentioned. So that superposition state can be stored in this way. So I will represent it like psi equal to alpha 0 plus beta 1. So that is a primary thing about this particular psi. So what is alpha and what is beta? Very simple, very straightforward, very easy. The deal goes like this. So alpha can be called as an amplitude, okay, amplitude of zeroth vector or state 0. Or simply to put, I simply call like alpha square as the probability of my state being 0. Now that is my alpha square. Now when I'm talking about beta, obviously it is what? Beta square is the probability of the state being equal to 1. So when I was talking about qubit, I said that the qubit can exist both as 0 and 1 at the same time, right? So that exists in a probabilistic manner. Meaning, for example, if I take any particular quantum state called psi, if I take any particular quantum state called psi as something like 0.2 naught plus, or I can say like anything. So I will say like 1 minus 8, whatever it is. It's like 0.8. So root of. So root of 0.2 get 0 plus root of 0.8 get 1. So the probability of this one. So the deal about this quantum state goes like that. So goes like this particular quantum state has the 20% probability of being 0 and has 80% probability of being 1. So that is given by this particular quantum state. Okay, so that is my representation of a quantum state or representation of a qubit. Classical, if you take any classical bit, I will name it as CB. If you take any classical bit, it will be either 0, CB equal to 0, or it is CB equal to 1. That's it. Either it can be CB equal to 0, CB equal to 1. But when you're talking about the quantum state, it goes like psi equal to alpha 0 plus beta 1. Meaning combination of 0 and 1 at the same time. Okay. So that is about this particular stuff. That is my quantum stuff. So this is how I will represent my quantum thing. Now, I will jump back to slides.
Sir, what is the main mechanism when taking square root, sir?
Simple. So why did I take square root means that? Why did I take square root means? So actually, 0.2 root is there now. So that is represented as alpha, and beta equal to 0.8 root. So why did I take root means that, so alpha square plus beta square should give me the output as 1. Alpha square plus beta square should give me the output as 1. Okay. So for that reason, we provide it this particular manner. So why? Because alpha square is, why? Because my alpha square is what? My alpha square will be 0.2 and my beta square is 0.8. As alpha square plus beta square should give me 1. So I simply took it in this particular format. That's it, nothing else. Okay. So that can be anything, but it will be in a form that alpha square, that is the coefficient of ket 0, the coefficient of ket 0 square plus coefficient of ket 1 square should always give you the output as 1. So why? Because we already know the sum of probabilities will give the output as 1, right? So that's the primary concept behind it. Okay. Now, so now let's go back to slides. So this is a representation of a particular stuff. Now, into next possible concept, that is my supervised learning. Okay, supervised learning in depth. Now the entire day will start like this. Or sorry, not supervised learning, it's superposition. Yes, sorry, my bad. So it's superposition in depth. Now, when I talked about superposition, it is nothing but what? The combination of the states in more than one place. Okay, or can I simply put like more than one particular stuff? Okay. So simply to put, a qubit can be in more than one particular state. So that is my superposition principle. Okay, when I'm talking about superposition principle, I can simply call it as a particular quantum state where I can have a particular quantum state where I will be having more than one possible stuff. Okay, a quantum state where I can have more than one possible output. Meaning, simply to put, I can say superposition like this. For example, let us consider you are going in a train or you are going through a car and you have two options, left and right. Okay. Now, classically, the probability goes like this. Either you can go through the left-hand side or you can go through the right-hand side. Okay. But you can't go both of them at the same time classically at this point of time. Right. Either you can go through the left-hand side or you can go through the right-hand side. So either you will take left turn or you will take right turn. But you can't take both of the turns at the same time, obviously. So similarly, when you're talking about classical bit, what happens is that the classical bit can only be 0 or it can be 1. It will be 0 or it can be 1. But it can't be, okay, it can be 0 or it can be 1. So simply think like that. Okay. But now let's go to quantum principle. So when you're talking about quantum computing, as I already mentioned, a particular quantum state can be in more than one particular state at the same time. Meaning it can be in 0 state and it can also be in 1 state. So meaning it's comparative, I can say, like when you're driving a car and you have left diversion or right diversion, you can take both the diversions at the same time. Until you can go through the left hand at the same time, as well as you can go through the right hand at the same time. Okay. So both of them you can cover at the same time. That is my simple superposition principle. Now comes the entire logic behind it. Now comes the entire logic behind it. Why exactly do you think it is used for? Why exactly it is important? Okay, very simple and very straightforward. Now let us consider solving a maze problem. Or let us consider solving a particular maze problem. where you have n possibilities to go and to find a goal state. That is my maze problem. Okay. When I'm planning to solve a particular maze problem, classically, let us compare it with the car taking right turn and left turns. So when I take the right turn or left turn, it is only one way to go. Okay. It is only one way to go. Excuse me for a while. Yes. So there's only one way to go, either right or left. Okay. But when you're coming to quantum phenomenon, as I already mentioned, you can take both left and right at the same time. Okay. So that's the primary deal behind. How it is going to help in actual computation? Very simple. So the deal goes like this. For example, let's go back to maze problem. The maze problem, man, you should be searching each and every way. Okay, you should be searching board. Yeah, you can consider board problem as well. Okay, so you will be searching each and every way. Like for first, you will try to go to right, and you will search to the right hand side. If it is successful, you are lucky. If it is not successful, you will come back and you will start with another way. So it will work in that way. Okay. Now, coming to your quantum principle. Okay, so now if you work like this, or if you're trying to search like this, like one way, second way, third way, fourth way, like that, you're trying to search each and every way in a lot of, like for a lot of iterations. Why? Because you're searching only one way, right? At a point of time, you're checking only one way. As you're checking only one way at this point of time, your probability of trying to get the answer will be complex. Not so complex. I can simply say like will take time. Why? Because if my answer is there in some 20th turn, if my answer is there in some 20th turn, then I should wait for 20 iterations in order to get my answer. Why? Because classical computing, I can iterate only once. Or I can go through a particular place and search only once. But when talking about quantum computing, what did I say? Because of the superposition principle of quantum, what happens? I can take, or I can be in more than one position at a point of time. I can be in more than one position at a point of time. When I said I can be in more than one position of a point of time, I can take both left and right at the same time. I can take the left turn and I can take the right turn at the same time. Now compare it with the maze problem. When you're talking about the maze problem, what will happen? I will simply, excuse me for a while. Yeah. Now coming to the maze problem. So in that maze problem, the answer is there in the 20th iteration. Okay, the answer is there in the 20th iteration or the 20th turn. So because of this quantum computing phenomenon, what happens? I can be, or I can check each and every iteration at the same point. I can check each and every iteration at the same point of time. Meaning I can go to the right, I can go to the left, I can go to the straight, and every possible turn at the same time. Why? Because of the superposition principle. As I already mentioned, you can stay in more than one state at the same time, right? As you can stay in more than one state at the same time, what happens? I can check every turn at the same time. So now, instead of searching each and every turn one by one and waiting for 20 iterations to go through my 20th turn, at this point of time, because of the superposition principle, I can simply check each and every turn or each and every turn at the same time. As I can simply check each and every turn at the same time, I can directly check the 20th turn in my first iteration itself. Why? Because of the superposition principle, I can check first turn, second turn, third turn, fourth turn, and so on up to n turns at the same time or in a single iteration. As I can make every search in a single iteration, comparatively, I can get to my goal state faster than my classical computing or the classical state. Got it? So classically, I took 20 iterations to reach my place. But in this point, I just took only a single iteration to reach the place. Okay? So that is the basic principle behind this superposition thinking. Okay? And this is why it is a huge advantage in quantum realm. Why? Because I will be having a lot of states. Okay, so when I was talking about an optimization problem, there will be a lot of things for the optimization problem, right? As there are a lot of things for the optimization problem, so in that sample space, there will be a lot of points. And I need to make sure that I'm checking in case dependent iteration. Same thing will happen. Even if you're working on the dependent iteration as well, so that dependencies will also be checked at the same time. Okay, so that's why it won't be a problem exactly. Okay, so it's the same checking only. So classically, you will check one by one. In quantum way, because of the superposition principle, you check everything at the same time. That's the simple deal behind it. Okay, it's not like which iteration will come our result. So same thing. Okay, so classically you check one by one, right? In quantum, you will check everything at the same time. That's the simple deal behind it. Okay, now, so in this way, we will be having an advantage compared to your classical stuff. Okay, now the deal goes like this. So that's what we call it as a quantum parallelism. Meaning, for example, if I have n qubits in superposition state, we can represent 2 to the power of n states at the same time. That is, classically, if I want to represent 2 to the power of n states, I need to have 2 to the power of n classical bits. Okay? But when I'm talking about quantum computer, if I have just n qubits, I can represent 2 to the power of n states just by using n qubits. Meaning, just by using 10 qubits, I can represent 1024 states. But classically, if I want to represent 1024 states, I need to have 1024 bits. Got it? So this is an exponential advantage which you can get by using quantum, just because of the superposition principle. Next main foundation principle, which I want to talk about, is quantum entanglement. So what do you mean by quantum entanglement? Okay. So what do you mean by quantum entanglement? Simply to put, very simply, let us take 2 quantum states. Okay, let us take 2 quantum states. And let us consider these 2 quantum states are heavily related. Okay, when these 2 quantum states are heavily related, I will separate them. I will separate them so that I will keep one quantum state with myself in the Milky Way galaxy. And I will give another quantum state to my friend who will be in Andromeda galaxy. Okay, Andromeda galaxy, not some other district or something. Now, what happens in this quantum entanglement is that the moment I measure the qubit of mine, so the moment I measure the qubit of mine, my qubit will definitely give an answer like 0 or 1 or whatever. It gives an answer, right? So the moment I measure my qubit staying in Milky Way galaxy, I can easily see or I can easily find the answer of the qubit which is being there with my other friend who is in my Andromeda galaxy. Okay? So you might be thinking, what is the deal behind it? Okay, completely all right. So 2 qubits, 2 quantum states are entangled with each other, completely all right. Or I can say strongly correlated with each other, completely all right. Now I will give 1 quantum state with myself and I will give 1 quantum state to my friend who is in Andromeda galaxy. Okay. Now, the moment I measure my quantum state by staying in Milky Way galaxy, I will get a particular output. And that particular output can be 0 or 1 or anything. Let us consider some. Okay. So the moment I measure that thing, what happens is that if I get my output as 0, I can say that the qubit which is there with my friend in Andromeda galaxy, that output is 1. I will directly say that. So he don't need to measure that as well. So the friend in my Andromeda galaxy, he don't need to measure that as well. Just by saying that minus, just by finding that minus 0, I can directly say that his is 1. Okay. How is this happening? Because of this entanglement principle. Now we might be thinking, okay, what is there here? Okay, what is the magic here? Okay, simple only, no, what's there here? Very simple. Think like this. Let us consider you have 2 coins. Okay, one in my right hand, one in my left hand. Now you toss 2 coins at the same time. And you got them. And you open the coin of your right hand. You got the output as heads. Now, by using this information, can you say what is the outcome of my coin in the left hand? No, I can't say that. Obviously, I can't say that because they both are independent actions, right? But if these 2 coins are entangled, then again I repeat the same process. And if I see the coin in my right hand, and if it gives me heads, then I can directly say that the coin in my left hand is tails, without even opening my left hand or without seeing my left hand. How I am saying that? I don't know how I am saying that. Just because they both are entangled in nature, I can say that. So that is the principle of entanglement. Meaning without disturbing, excuse me for a quick. Yes, sorry for that. Now coming back. So how it is being there? Very simple. When these 2 coins are entangled, they will be very heavily related to each other. And as they will be very heavily related to each other, something will happen. We don't know what is that something, but something will happen through which we can say that the output of one thing influences the output of other thing. Got it? The output of one qubit influences the output of the other qubit. And that is my entanglement in nature. Okay. Why it is important? Very simple. Or why it is mysterious? Very simple. First thing, how 2 coins actions can be related. So by seeing the coin on my right hand, I cannot see the output of the coin in my left hand, right? I can't do that. But if they both are entangled in nature, I can do that. So how I am able to do that? We don't know. It's the mystery. Second mystery comes here. When I said 2 qubits are entangled in nature, and 1 qubit is with me, and 1 qubit is with my friend who is in Andromeda galaxy. What is the distance between the Milky Way galaxy and Andromeda galaxy? Approximately something like 300,000 light years. Okay. So when I say 300,000 light years, then what will happen? What is the meaning behind 300,000 light years? Meaning is, you guys know obviously. So real-time computing example. Yes, I will say that. I will come to that thing as well. Now, so when I say 300,000 light years, it will take approximately 300,000 years even for light to travel to Andromeda galaxy. So light is the fastest thing which can move in this universe. But even it takes light 300,000 years in order to reach Andromeda galaxy. Okay. Now, in that case, Einstein says that, no, not complete physics says that the fastest thing in the universe is light. The complete physics says that the fastest thing in the universe is light. Right? Now, if I measure my qubit in Milky Way galaxy and it gives the output as 0, I can directly say at that instant itself, I can say that the qubit in my friend's hand in Andromeda galaxy's output is 1. How I am directly saying that at that particular instant itself? Why? Because if I get the output as 0, Now that zero should travel to that qubit with my friend in Andromeda galaxy, and that can influence his qubit. Okay, it makes sense. But in order to travel, like in the time taken for this information to travel to Andromeda galaxy takes approximately 300,000 light years. Yes, both qubits can be in same state. So they come under, what can I say? They come under the type of entanglement which we are doing. So they come under the type of entanglement which we are doing. So yeah, it won't be a problem. So the type of entanglement can be two ways. One is same, and second thing is different. Meaning in one type of entanglement, what will happen is that if one thing is zero, the other thing is also zero. If one thing is one, the other thing is also one. In the opposite, what happens? If one thing is zero, the other thing is one. If one thing is one, the other thing is zero. So that comes under the entanglement type. Got it? So that's the deal behind your entanglement nature. Now, where do we exactly use this thing? Very simple. It is essential when you're talking about quantum communications and quantum cybersecurity. How exactly in quantum communications? Very simple. I have my qubit here, you have your qubit there. Now what I will be doing, really if I want to pass any information, what I should do? I should send all my bits to you, right? I will say hi. And that hi bits, the bits which is carrying that hi information should be traveling to you. Okay, and then you'll be receiving that information. That's how it works, right? But when I'm dealing with quantum computers or quantum-based communication, what I will do means entangle the two qubits first. I will entangle your qubit and I will entangle my qubit. And then what I will do, I will simply say hi to my own qubit. And then I will tell you to measure. You have your own qubit, so you will measure. You'll get the information directly. I don't have the time or I don't need to go through the stress or the work to send my information to you. I don't need to send my qubits to you. What I will be doing, I will be simply entangling your qubit and my qubit, and I will measure my own qubit, and I will tell you to measure your own qubit. You'll obviously get the message from myself without me sending you the bits. Okay, so in this way, what happens is that the communication becomes faster. In this way, the communication becomes faster. That is the first thing. Second advantage, quantum cybersecurity. Now, we know about this guy called as an eavesdropper, right? Who is a hacker, who is trying to see my information, who is trying to search my information. Okay. Now, what will happen is when I'm talking about search my information, if I save a secret message to one of my, colleague or someone, we are trying to do a very huge secret stuff, and I told one of the secret message to my colleague. Now there's an enemy or there's our competitor. And what he will be doing classically, he will try to get the transmission data. He will try to get the transmission data. Like I will be talking in phone with my friend and stuff like that. Nah? So he will try to get the transmission data from the signals. And he will try to get that data. And after getting that data, what he will be doing, he will try to decode it. And he will get the information. Neither me nor my friend will know that our data is breached. Okay, that is my classical communications. Now, when I'm dealing with quantum communications, what will happen is that directly to put, I will say that I will transfer my data in qubits manner rather than a bits manner. Instead of sending my data through bits, I will send my data through qubits. Now, what will happen? As I already mentioned, if I measure one qubit, if it is entangled in nature, if I measure just one qubit, then what will happen? The other qubit measurement will also be known. That's what I told right now, right? So simply to put, if I disturb one qubit, the other qubit will also be disturbed. That's what I mentioned about the entangled qubits, right? Now comes the clear deal here. Now if I'm trying to send the information through quantum bits to my colleague, okay, and let us consider a third party guy or a hacker who came to grab that information. Now what he will be doing, he will try to grab that information, and he grabs that information. After grabbing the information, he will try to measure it, right? The moment he measures that thing, what happens? my entangled qubit will also decompose, or my entangled qubit will also be measured. And as my entangled qubit will also be measured, what will happen? I can easily get that thing and I will get to know that, alright, this is already being measured. I can say like that, right? So when if that particular thing is already measured, I can directly find that some third party guy tried to take my data, and they will simply eradicate or destroy that particular data. Got it? So in this way, I can clearly find who is trying to take my data. So that is the important concept when you're dealing with the quantum communications for the quantum entanglement stuff. And the mystery of quantum measurement. So this is also one of the main thing which I always like to say about. So quantum measurement means what will happen, simply to put the thing which I'm trying to say. The moment I measure a particular quantum state, how does a classical data encode? Yeah, that's a big concept. So you'll be learning about it in the next sessions, I guess. But yeah, yes, there are no algorithm to encode, but there is some techniques to encode. Like you'll be having basis-based encoding, angle-based encoding, amplitude-based encoding, and so on. So you'll be having encoding techniques for that. Now, mystery of quantum measurement. Very simple, very straightforward, very easy. Okay. So the mystery goes like this. The moment I measure a quantum state, it will decompose. Okay? What do you mean by this measurement? Very simple. Before measurement, a quantum state exists in a superposition state. Okay? And then before I observe or before I try to measure, the quantum state exists in a superposition state, meaning the combination of both 0 and 1. But the moment I measure a quantum state, what happens is that it will decompose to any one state. That is either my 0 or my 1. Understood? So that is the principle of my quantum measurement. When I am not measuring it or when I am not observing, it will be in a superposition state. But the moment I observe it, what will happen? It will decompose to any one of the state. That is either 0 state or 1 state. Understood? So that is the principle of the quantum measurement. So that's why we cannot measure and what can I say that? A superposition state. Our output will not be a superposition state always. Now, the next deal is about quantum gates. So I don't like to explain this in a detailed way, the quantum gates, but I will simply directly say the normal stuff regarding the quantum gates. So what exactly do you mean by quantum gates? Simply to put, classically we have something called as a logical gates, right? Classically we have something called as a logical gates. And what will the logical gates will do? The logical gates are responsible for performing some operations on my classical bits. I have a classical bits, I have my classical bits. Now, if I want to perform any sort of operation for that classical bit, I will be using a gates, or I will be using the logical gates like AND gate, OR gate, NOT gate, and all the stuff. I will be using that. So, in order to perform the measurements or in order to perform some processings on that classical bits. Similarly, if I want to perform any type of transformations or any type of stuff when I'm dealing with the quantum bits, that is my qubits, I'll be using something called as quantum gates. Okay, I'll be using quantum gates. And these quantum gates are responsible for transforming the quantum state. The quantum gates are responsible for transforming the quantum states and to provide me the final answer or stuff like that. Some of the important quantum gates are poly X, poly Y, and poly Z gate. And we'll be having the 2 qubit gates which are called as C0 gate and controlled Z gates. And then we have Toffoli gates and all the gates as well. Okay, but the main gates which we'll be using is X gate, Y gate, Z gate, Hermat gate, and we'll be having C0 gate and Toffoli gate and CZ gate. Okay, so these are all the gates which we'll be using for quantum transformations and stuff. And one most important thing to identify is that when you're talking about classical gates, you'll be talking about Boolean logic, meaning 0, 1, 0 or 1, 1, 1, like that. But when you're talking about quantum gates, you will be talking about the matrices-based transformation. Okay? Classical gates depend on Boolean transformation. Quantum gates depend on matrices based transformation. Got it? So that's a primary idea behind it. Now, Hadamard gate. Why I'm explicitly telling about Hadamard gate is that if I want my quantum state to be in a superposition state, I want my quantum state to be in a superposition state. At that time, I'll be using the Hadamard gate. The Hadamard gate will be the one which changes my single state to quantum state, superposition state. So at the starting of the circuit, every qubit will be in a zero state. At the starting of the circuit, every qubit will be in the zeroth state. Now, if I want to bring that zeroth state qubit into a superposition state, I'll be using my Hadamard gate. And this Hadamard gate will be responsible for converting that zeroth state into a superposition state. Got it? So that's a primary idea behind it. Now, how I can use or how I can create an entangled state? Very simple. First, I will apply a Hadamard gate, and after applying a Hadamard gate, if I apply a CNOT gate, then I'll get an entangled state. Okay? So I know this might be confusing, but that will be covered in the further sessions, so it won't be a problem. Okay, but I'm just trying to give a normal glimpse. Okay, now quantum algorithms. So some of the important quantum algorithms to identify. Some of the important quantum algorithms to identify are the Grover's algorithm, Shor's algorithm, and the circuit design principles, which are not required. So main thing is Grover's algorithm and Shor's algorithm. So Grover's algorithm is used to search the element from an unordered set. So if there's an unordered set, and in order to search any element, it will take O of n iterations. Or I can simply to put O of n time complexity in order to search any particular target state from an unordered set. But by using Grover's search algorithm, I can simply search that particular target state from an unordered state by just using O of root n iterations. Okay, so by just using the O of root n iterations, I can directly find or the targeted state from a particular unordered set. So that is the primary deal behind my Grover's algorithm. Quadratic speedup will be provided. Now, Shor's algorithm. So what will happen in Shor's algorithm is that the main thing about the RSA algorithm is prime factorization of two guys or something like that. So you'll be having a very big number, and the prime concept is to prime factorize that big number, and using those two prime numbers in order to solve a particular, or in order to create a particular key, and that key will be used for the communications and all the secret stuff. Okay, now by using this particular Shor's algorithm, I can directly find the two big prime factors from a big number by using this particular Shor's algorithm in a faster manner. So that's a primary concept which we will be observing when we are dealing with this Shor's algorithm. Now, so the challenges and opportunities. This is the last slide of ours. So when you're talking about the challenges and opportunities, first main challenge is the decoherence in nature. Meaning the superposition state which I'm talking about is very sensitive in nature. Literally very sensitive. What do you mean by very sensitive in nature? Very simple and very straightforward. Meaning it's very hard for me to maintain that particular qubit in a superposition state. It's very hard for me to maintain that particular qubit in a superposition state. Okay? Now that's another important thing. Okay, now comes the main thing. So the main challenge is I cannot let my qubit be in a superposition state for a long time. Why? Because it is very sensitive in nature. Meaning it is even sensitive by temperature waves. Okay, so that's why the first hardest thing for me is to maintain the superposition state of my qubit. That is my first main important thing. And the second main important thing is the hardware constraints. The hardware is very high. The requirement of hardware is very high for my particular qubit. So that's why that's also one of the important concepts. So the active research in overcoming these things are in my error correction codes. So these error correction codes are used in order to preserve the quantum information from being destroyed or from being decomposed. So what do I say when I talk about quantum information is that the superposition state information is there, right? So the superposition state information is known as my quantum information. Now I need to make sure that I am preserving that quantum information. Okay, so that's a primary deal behind it. And in the future, we will try to provide a lot of algorithms which provides exponential speedups and all the deals when I'm talking about machine learning and all the stuff. Okay, so this marks the end of my presentation regarding this quantum thingy. So yes, if you're having any queries or anything regarding this one, you can ask me, right?
Yes, participants, you can ask the questions. So any questions from the participant side?
Yes, I will be sharing these slides to Mr. Agorumuthu, so he will be taking care of it.
So you can find all the PPTs, all the documents related to this Qiskit Fall Fest in the GitHub. They'll be uploading once festival is over. So and you can also view the recorded sessions in YouTube Live also. Qiskit channel. So any questions from the participants? If not, we will wind up the session.
Okay. Quantum interference means simply to put the same interference which we will be seeing in the waves. So meaning, as I already mentioned, the quantum states are there. Now. So the superposition states or the quantum states will be represented in a wave-like structure. Okay. So what happens is that, so I need to make sure that my interference will happen, but decoherence will not happen. Simply to put, coherence and coherence should happen and decoherence should not happen. So decoherence meaning is cutting off the same amplitudes, thereby making it a straight line, meaning destroying the quantum state. And coherence means increasing the amplitude of the same thing by adding up, so thereby increasing the probability. So quantum interference simply says that the wave nature of the quantum state. That's it. Tensor operations of qubits. Yes. So why we will be using tensor operations on qubits? For example, as I already mentioned about the gates, the quantum gates work with the matrices-based concepts. Okay, as the quantum gates work with the matrices-based concept, what happens is that if I apply more than one gate, what will happen? I will make the tensor product of gates. And after making a tensor product of gates, I will apply this quantum state to my gate by using the, what can I say, that tensor product. We won't be using a direct multiplication. We'll be using the tensor product. We will not be measuring the superposition. We cannot measure the superposition. So the meaning you measure superposition, it will decompose to one of the bases. Quantum communications. So simply to put, I will communicate with respect to quantum bits rather than the classical bits. That's the first meaning. And what is the advantage of it? Very simple. So when I measure with quantum bits, that is entangled qubits, what will happen is that, simply to put, the moment a hacker or an eavesdropper will measure one of the qubit, because of this entanglement nature, the entangled qubit will also be decomposed. So the moment my receiver receives this entangled qubit, what will happen? He will easily identify that this particular qubit is already decomposed. Now, as this particular qubit is already decomposed, what will happen? He will find out that some other third party guy tried to take out my qubit, right? So in that way, he will find that there's a hacker or something. Automatically, very simple. If I want to make my quantum state to be in a superposition state, because at the beginning of the code, the quantum state will be in a zero state only. Now, if I want to make my quantum state to be in a superposition state, then I will be using the header method. Okay. What is error correction? Why is error correction? It's very simple. So, because what will happen is that the quantum information is there. Now, the quantum information will be sensitive in nature. So, it will be easily decoded or easily destroyed or easily decoded. In order to preserve the quantum information, we will use something called as an error correction. And by using this error correction codes, what happens is that I will preserve the particular quantum. Okay? So that's the
Question.
Can we decide which superposition state
Session.
we can do that. So we'll be doing that by using different quantum gates and stuff like that. So the quantum circuit measurements of that. We will be getting the accuracy by using probabilities and then simply to put the probabilities. That's it. I hope
Any more questions?
Okay, by using the probabilities. Yes, by simply using the probabilities, that's one way. And the other way is you simply decompose it. You decompose them and you have a measurement, right? And then you will be taking care of it. No. We cannot do that. We cannot measure a quantum superposition state.
So I hope there are no more questions from the participants.
Okay, cool.
Okay. So thank you. So good evening, everyone. On the behalf of organizing committee of Qiskit Fall Fest 2025 NIT Puducherry, I take this moment to express our heartfelt gratitude to Dr. Nyan Allah for delivering an enlightening and thought-provoking session on Introduction to Quantum Foundations. Dr. Nyan, your session has provided our participants with a crystal clear understanding of core principles that power quantum computation, from the beauty of superposition and entanglement to the conceptual depth of quantum states and measurement. We see your ability to simplify complex ideas, connect foundational theory with real-world applications, and inspire curiosity has truly elevated the learning experience for everyone presented here. Also, you have set an excellent foundation for the sessions that will follow over the next few days. We sincerely thank you, sir, for taking the time from your schedule to guide us, motivate our learners, and contribute to the academic strength of this festival. So it is an honor for me to have you with us, and we look forward to the future interactions and collaborations. Once again, thank you, Dr. Nyan Allah, for a truly insightful session. Thank you so much, sir. And with this wonderful session, we officially wind up day one of the Qiskit Fall Fest 2025. Before we conclude, I kindly request all the participants to join us for the day two by 5:45 p.m. As the sessions will begin exactly at 6 o'clock by tomorrow. Tomorrow, we are privileged to host three exceptional speakers who are active and budding researchers in quantum computing, who will share their expertise and exciting work with all of you. Thank you, everyone, for your enthusiastic participation throughout the session, and have a great, wonderful evening, and see you all tomorrow. Thank you.
Yeah, thank you, everyone. Thank you.
Attendance link, sir. சார் அவங்க வந்து நைட் 10 o'clock வரைக்கும் இங்கே தான் இருப்பாங்க சார். நாகேஸ்வரி மேம்லாம் நைட்டு 10 o'clock வரைக்கும் இங்கே தான் ஒர்க் பண்ணுவாங்க சார். நான்